All right, so good evening. So today's topic is electric potential. You would have done a lot of stuff on electric potential, like electric potential due to a single charge, electric potential due to multiple charges. And I've been repeatedly saying it's the easiest one because the electric potential is a scalar. So whatever is a charge configuration, if it is individual, it's a combination, it's a continuous charge distribution like a rod, ring. You just need to add the potential. That makes your life pretty simple. So today's question is a bit complicated question, but you will find it very useful for NEET examination, JEE mains examination, AP Physics, IB board, whichever part of the globe you are, this is going to be interesting for you. Uh, I will break down the problem, but let's read the problem first. In my playlist of electric potential, you already have a lot of conceptualization, you have categorization, and the analysis of the questions. Please don't forget to subscribe to this channel because you will see some excellent questions being explained in a very lucid manner. So, the explanation is the key of my channel. I tend to give a lot of detailed explanation, which will help you score well. Let's talk about this question now. All right, so you have this um, wire. So you had a wire, and this wire was changed into a particular shape, which you can see behind me. And it's a uniformly charged wire. And the question is you have to find the electric potential at the center of the semicircle, right? So this is of finite length. So this is of some length 2r, this is 2r, and this overall is radius is r. Let's say the charge, which is density, the linear charge density available to you is lambda, which is in coulomb per meter. Okay. Now this is your given data. Well, let's see the concept. Let's do the process of conceptualization. Now, generally, when you get a question of potential, if I go back to my concepts, the first thing that comes to my mind is, okay, I know potential. The simplistic potential I know is due to a point charge, which is given by VR is equal to K Q by R, right? And this is a point charge at a distance R. Okay, at a distance R, you have to find the potential, right? This is the simplest thing that comes in your mind. And if you have multiple charges, you can find the electric potential due to all of them at a certain point using this. You just need to add V1, V2, V3, V4. You know the distance of that point where the charge is to be found out from each charge. Add it and you get your answer. But when I do the conceptualization process, I don't see a point charge. I don't see multiple charges. What I see, on the contrary, is a continuous charge distribution. And within continuous charge distribution, I see two geometries. First geometry is my linear geometry. This is my linear geometry. And this is my semicircle geometry, right? So there are two geometries. So I've already categorized this in my mind that I'm dealing with continuous charge distribution. And this continuous charge distribution has two geometries. The basic of potential is this, right? The only thing is now how do we approach when we have continuous charge distribution? So let's say because uh, the rod is long, so I'm just concentrating on this part of it. This is symmetrical, so whatever answer I get for this particular rod as a potential at the center, the same answer will be valid for this. I can add these two as numbers. So I'm just going to concentrate on the single rod first. Now, from what I know from the analysis point of view, if I have a continuous charge density, I tend to solve my problems using the process of integration, right? Which is picking up small, small charges and then calculating small, small potentials because of those small charges. And then integration is the technique to find the sum of all these small dVs, right? So I will just write a dV for your benefit. So let's say I pick up this particular dx as a small part of this rod, and this particular one, right? Because the total charge density is lambda. The total charge on the rod, okay? So the total charge on the rod, okay, on the rod is equal to lambda multiplied by 2r. That's my total charge, okay? The charge on a small length dx will be given by dq, okay, will be given by lambda multiplied by dx, right? So you have a very small uh, length being taken, and I've calculated the charge due to that. I try to find the uh, electric potential due to this small charge dq at the center. Okay, let me find it. And let's say this distance is given by from here to here is given by x. Okay, so this distance is x. So my expression for potential, which is going to be dV now, changes to dV is equal to k dq, right? The distance of dq from the point where the potential is to be found out is x. So I add that, and this is equal to k multiplied by dq, which is lambda dx by x. So I have found the expression of small potential due to a small charge at a distance x, which was given to us, right? We were told we have to find at the center of the semicircle. So this is my dv. But let's think in terms of x. The charge starts from here, right? This is a point. Let me call it A. The charge starts from here, right? Which means the x has a total length from A to O. Okay? Because I have to do integration, I need to know my limits. You can watch my videos on definite integration because I also teach mathematics. Please have a look at definite integration. Okay? So we're finding the upper limit and the lower limit of x. So I'm going to write v is equal to the lower limit. Let's say this is the short, the continuous charge ends here, right? So this distance is r, right? And this distance is 2r plus r. 2r plus r, right? So this is your 3r. So I'm going to write k lambda dx by x is equal to k lambda natural log of x. I hope you understand logs. I have a video on this playlist that explains the properties of the log, because if you have good maths, it's easier for you to do analysis part of the physics. All right, so this is k lambda log x, and this varies from r to 3r. So if I do this, this is k lambda log of 3r minus log of r is equal to k lambda log of 3r by r. I'm using the properties of logarithm logs, so I get a log 3. So my answer is k lambda log 3 volts. Okay, this part done. Okay, and because of symmetry and the potential being a scalar, this part also gets added, right? So whatever is the potential due to this at O is the potential due to this at O. So I just need to double this, and that's all. Okay, so now the doubling is going to happen. So I found the V due to this rod. The total potential due to both the rods is going to be twice of this. So total potential due to rods, okay, rod 1 and the rod 2 is equal to 2k lambda log 3 volts. So one part of the puzzle is solved, and now we will focus on the second geometry, which is the semicircle. No brainer, very simple. Again, the basic conceptualization process starts from here. And the only difference is this is applicable to a point charge. I have a continuous charge distribution. I am applying the same concept of the potential on a continuous charge distribution uh, by using a mathematical technique called as integration, right? So let's pick up some part of it. So let's pick up a small part of this semicircle. Let's say this is dx. Okay, this is dx. The potential due to dx will be, and dx, by the way, because this is again a case of linear charge density. We know the charge density is how much. So the total charge is going to be q is equal to lambda multiplied by pi r. Okay, so the circumference is the length, right? So this is the total charge which is available on the semicircle, right? We know this. On dx, how much charge will be available? That's a point, right? So I know my lambda is equal to so I need to find on a very small dx, right? In the same way. So I will find dq is equal to lambda multiplied by dx. And I know what is the value of the lambda is known to me, right? So lambda is known to me. So I don't need to worry about it. So I just write it as dq is equal to lambda dx. But this is important, right? Gives you a good analysis of that. This has a different charge, and the circular geometry has a different charge, right? That's a value of this expression. Now let's talk about dv for the semicircular ring. dv is equal to k dq divided by r. Okay, so we already know what is r, the distance at which you have to find the potential from here. This distance is for all the small is for all the small segments, which I mean, right? You take any segment, this distance is r. Now, when I write this, I need to do something which is integration, right? So I will just integrate this. V is equal to, so it's, let's say it starts from 0 and this will end at pi r, right? So that's a dx. The lower limit of dx is 0. The upper limit of dx is pi r. So this is 0 to pi r, and this is k dq by r is equal to k. dq can be written as lambda into dx divided by r. See, the difference between the rod and the semicircular is visible now. You don't have an x here, right? Because the distance is constant of all the small segments. You don't get an x in the denominator, which you got in the case of the rod. In a rod, if you take this segment, its distance is different from the distance of this particular segment. But if you take a arc like this semicircular, the distances are common, and therefore you get an easier expression actually. Okay, so you get k lambda by r into x, the upper limit is 0 to pi r, is equal to k lambda by r, and this is pi r minus 0. So r gets cancelled, and you get a k lambda pi volts. That's your expression for the semicircular ring. Now, the beauty of electric potential is you can add electric potential like number. It's a scalar, right? You don't have to worry about I, J, K, etc. But nonetheless, please go through my playlist on vectors if you want to score well, because without vectors, it's futile to do physics. So you should know which vector technique is to be applied when. In the chapter of electrostatics, you will have to use vector at many places. This is an escape. We did not have to use vector anyway because potential is a scalar and I just need to add it. So therefore, my total potential is 2k lambda, okay, ln3 plus k lambda pi. I can take a k lambda common. I get 2 ln3 plus a k lambda. It's a pi, okay? So plus pi. That's my answer. That's my answer. If you see my conceptualization process, I did not get scared because this was a continuous charge distribution. How will I do this? Many ideas came to my mind. I took the simplest one, which is the basic definition of a potential. The second conceptualization I did was it's a scalar. And that helped me solve the fact that these two rods are identical, so I can directly add the potentials due to them. And then the semicircular ring was a cakewalk. I think it was pretty straightforward. Had it been a complete ring, I would have doubled it. So that's the way you need to solve problems. If you get a problem in NEET examination, or you get a problem in JEE Mains or AP Physics or IB Board or Cambridge or Pearson, whatever O level, advanced level, beginner level, if you get a problem on potential, just think in terms of the basic concept and the fact that it's a scalar. I have numerous videos of potential available on my YouTube channel. Please subscribe to this channel if you want to see some fantastic numericals and problems. Uh, the difference being, this channel emphasizes on explanation. I'm not giving you, a mere solution that this is the way you need to solve, right? It's your problem to understand it. I'm giving you step by step understanding and explanation of how to do this problem. So thank you very much, guys, and wait for my next